We're back for more. And we're going to share, hopefully successfully. Looks like we've got the reverse reaction going here. Yeah, this is using NAD+. I didn't write it down on our previous screen, but I said it. NAD+ in this one's becoming NAD. Okay, I'm not circling my plus apparently. NADH. And in the previous one, which was actually out of order, so yeah, here in the previous, and this one, NADH is becoming NAD+. NADH is a reducing agent. That's what happened, a reduction of a ketone to an alcohol. NADH, sorry, NAD+, this was NADH becoming NAD+, reducing the ketone. This one is NAD+, oxidizing probably an alcohol. And there's an alcohol becoming, well, interesting. We'll have to figure out what's going on here. We re-aromatized and we lost CO2. Where's the CO2? I think that has to be the CO2. Yeah. 3 points. No intermediates. Wow. Okay. Please realize you need a new H here. It's a CH2 right now, and it used to be a C with one H. So there's a new H there. Where did it come from? Somewhere here. What H's are being lost from this molecule? Let me narrow it down. There's an H here that's not in the product. And the H here is also not in the product. How do you want to roll with this? I can kind of see this happening either way. But one of those H's is a pretty good acid, right? So I'd lean towards starting this with an acid-base mechanism. Carboxylic acid reacts like an acid. Why don't we start with that? Enzyme has lone pair, act like a base. There's your CO2. What are you going to do with this sigma bond? You want to make a good argument that pi has to break before sigma? You want to do that? I'm going to do that right now. Blue second. I also have a good argument. Sometimes maybe you don't have to wait for the pi to break. And I don't know how much you want to know about that. Because you're forming a gas here. That's a very strong driving force for a reaction. Entropy driven. Sometimes you don't, the molecule kind of sees its fate and it becomes gases without waiting for pi's to break before sigmas. I don't know. Ignore what I just said. It's just words. That's going to make a pi. This is going to make a benzene. Driving force again is to become aromatic, right? Well, that looks terrible. I like the thicker arrows here. I think I'd have figured this out within 15 years of using Starboard. Here we go. Yeah, and the sigma bond's going to break and attack the... This is all arrows, everybody. Hey, there's a second H for that carbon. What do you want to do with this pi so it ends up down here? Resonated, of course. What do you want to do with this old pi so that it becomes this lone pair right here? Resonated, of course. How terrible is that? Not bad. I probably would give maybe 3 out of 3 if you had attacked using the enzyme this H, resonated in here, resonate in here, resonate in here, and have hydride from here attack up here. That to me shows you understand the flow of electrons. Everything's reversed, base, enzyme base grabbing this, and this H minus attacking there. I would accept that. This makes a little more sense to me because this is an acid base to start off with a clearly not a strong acid, but an acid. It's called a carboxylic acid, for crying out loud. Okay, now I don't know how clear I can make this. I know we're stressed at this time of the semester, but if you look at one exam previous to this, where it says this is Dr. Whitaker's absolute favorite mechanism and it's going to show up on every test for history. Okay, I'm making that the official record right now, this video right now. I'm always going to put this reaction on an exam. This is biochemistry at its best, and it has so much 242 review in it that I just love it. So let's go with that. Where's tyrosine? Tyrosine. That's one of the amino acids. I'm going to draw it, but I'm not going to be drawing this again even once. It's part of tyrosine. You see that on your handout. No, we already have an R on this page. We call that R prime. And tyrosine has the R prime attached to CH2, attached to a C that has both the NH3 plus and CO2 minus. There be your tyrosine. So clearly that nitrogen's ending up on where the carbonyl is. And it even tells you, make an imine first. I'm going to leave these 3 clues there too. If I change these molecules around, is that going to mess you up? Change to a different ketone here and a different amine here? Because I can find a biochemical reaction where the same process happens and you get a different amino acid and you get a different side product. And I'm going to do that. Does it change this mechanism at all? No. First up, imine formation, chapter 16. I told you I love this. We're going back to the start of 242 right here. Why we learned this in the first place. I'm going to change that to NH. Well, here, I think one way to do it is scribble out H2 and draw them both with bonds. Made that a little tight there. And there's a lone pair on this O. And that's gonna be an NH2 plus now. So it's gonna reach and grab, it can't reach. It's too tight. It's gonna grab that H. And we're gonna dump a lone pair on the nitrogen. I don't like how that worked. I think that's clear. And what do we do when we can't reach that H? We got to sneak in the word intermole. I got to have a real tiny intermole here. Intermole. How much can I shrink that down and not still be able to read it? Can you read that? Of course you can. I can't move it though. It's too small. There it is. I'm putting it over that arrow. Oh, I like how that looks. Save. Okay. So we're going to draw our intermediate here, a hydroxylamine. Whoa, I don't know what happened. Forward, I think. Yeah. We've got R prime in green. We're going way over here, folks. I haven't used any room over here. R prime. CH2C that now has an O with an H on it. Also has an N with an H on it. Pushy. Can I do a circle? I think I only need up to the nitrogen. R double prime. Okay, the N has R double prime on it. And most importantly, lone pair. Pushy. They can push off a crappy leaving group. Red. Hey, starts in the middle of the lone pair. Computer is really giving me a hard time. There we go. Hydroxide leaves. Probably not so much in biochemistry, but you know, I'm okay with it. I just want to be consistent with chapter 16 and not change anything on you. R prime is now attached to a CH2C and double bond to N. H, R double prime, and pink. Don't forget that's a 4 bonds to nitrogen. Cat ion. Everything, it seems a little small. I think that is everything. Yeah. Good stuff. Ready? So we've done the imine. That's not an imine. We're not done. We can make it done. Hey, the next step would be removal of this H, right? What's my best base around that I already had around? I can use ends with a lone pair. Put it in, I don't know, orange. Ends with a lone pair in baby blue. Come and grab that H and make an imine. Imine formation is over. Time for tautomerization. Sadly, we don't have enough showing in our molecule. I should have been a little more judicious with my R labels. Where's the tautomerization gonna go? What have we made? Well, I'm looking over here. We got a double bond between nitrogen and a carbonyl. Yeah. And it looks like, let's see, change that, yeah. Oh. There's gonna be a carbonyl alpha to the glue. There's glue. That's gonna end up being a carbonyl. Tautomerization. Hydrolysis. I'm wondering if hydrolysis gets us to the answer. Let's draw. Let's just see what hydrolysis does. That may be a mistake. I'm gonna draw it though. I know R prime doesn't change. And the double bond to N doesn't change. And the R double prime, let's see what it looks like. We have an N bonded to a C that's got a CO2 minus and 2 CH2s off the same C to another CO2 minus. Oh, we do need tautomerization. We need the double bond to not be here, but it to be here instead, so that we can do hydrolysis here to get a ketone on this position. I need the double bond to be here so I can do hydrolysis of that imine. So when I said tautomerization, I'm going to go from one imine to another on the other side, which is remarkably easy in this example because it's an alpha position. That's alpha to a carbonyl. Do you agree? So it should be easy to take that off with an enzyme. Enzyme's going to take, and the conjugate acid's going to protonate. One step tautomerization. They always are one step, aren't they? Go red. Grab H. Make a new imine. Get rid of old imine and protonate the position. It is tautomerization. We're almost there. Hydrolysis, we're going to have a molecule right here, CH2C. We have a single bond to N that has an H now. And the double bonds on the other side. Wait, the H one on the carbon. My apologies. And the double bonds on the other side. Pink. CO2 minus. CH2 once, twice, CO2 minus. I'm going to do something temporary circle here in or highlighter. Here's a highlighter, temporary. Sure. I'm going to go with blue. So you see this here is the same as this here, except you have an O where you used to have an N. So hydrolysis would do that for you. I'll leave it highlighted. Doesn't hurt. And we're gonna go down a little, just need to see those two products. Hydrolysis, we're gonna introduce an oxygen to that position. We're gonna be losing an H from the water, not right away. Attack the imine. Lone pair on N. Needs to protonate that N. It's gonna be an NH3 plus when we're done. So we got a lone pair on the end that we can protonate using HNs. What color was HNs last time? We have an orange H for N. Doesn't matter what color. And baby blue, we're going to protonate that. And anything else we can do? We can make, we can neutralize our oxonium that you just made. This would make an oxonium. The red arrow, the first red arrow, makes a third bond to oxygen, which is an oxonium. Oh, don't use red though. Don't use blue either. See, the last thing that happens is neutralize your oxonium. Okay. What do we got? We got R prime. Wow. We have R. Hello. Okay. Goes up to a CH2, goes to a C, goes to an NH. The NH now has a single bond to a carbon that has a pink CO2 minus. Really doesn't like the bottom of the screen today. CH2, CH2, CO2 minus. We got that. We have an OH on there. I think it's time to eliminate and make the 8 into a better leaving group by protonating it. HNs can protonate the nitrogen first. But I had orange. I was mistaken. Lone pair, protonate to make a better leaving group. Okay. And to make it leave, you can use HNs, the conjugate base thereof, N's neutral, lone pair. Grab the H off of the oxygen, eliminate into a pi. And if you really want to make the NH3 plus, you could protonate the N. If you don't, you can do this in any amino acid mechanism. You don't have to end with NH3 plus. You can end with NH2. It's just a different acid-based version of tyrosine, isn't it? It's still tyrosine. Or you can protonate the nitrogen with H enzyme when you're done. And that's that. Yeah, a lot to it, but so much good review that I can't resist it ever. And it's called transamination if you're curious, and it's how you get from one amino acid to another often. We made this into tyrosine, and we made glutamic acid, which was another amino acid, into this, the carbonyl. And that's all for this one. We're going to be coming back, not on this page because we did this one already. No, we didn't. I think I have 2 copies of something and one's blank now. Yeah. NAD plus, NADH comments are for what we just did. And then we're going to come back and do this lovely little problem here, which this one's almost free points, everybody. You're going to like this one.
Yeah, okay. Thank you.
Sorry, we got a question before we switch this off?
No, no.
Okay, I'll be right back. Trying to quit, not letting me.